Hello and welcome to this lecture. In the previous lecture, we saw a lot of standard hypothesis tests, right? In the theoretical sort of framework, you're given samples and testing for mean, testing for variance, comparing mean, comparing variance, goodness of fit, etc. Now we'll turn the table a little bit. We'll ask a few questions involving data. So there's some data, and you want to find out something about the data, or come to some conclusion, or do some develop a hypothesis which you want to test out using data. Okay. In those cases, how does a hypothesis testing type situation fit? How do you get a null hypothesis? How do you get an alternative hypothesis? And what is important in metric and measurement? Is significance level and power, are they enough, or do I need something else which is also important? Okay, so let's get into that. This will be once again a slightly high level lecture. I'll go through it a little fast. No major equations or so in this lecture, but it's important to understand because this motivates the need for this p-value, and which is very quite important in the area of hypothesis testing. Okay, so when you start a statistical analysis problem, you have a bunch of data. Maybe you know a little bit about the data. Maybe you can get some descriptive stats, mean, variance. You centralize it, you normalize it, you do histograms. Maybe if it's too vast, you take log. You do various things that we've learned so much in this course about how to deal with all these parameters and all that. Maybe you try a few estimations, or who knows. You try all that. Okay, so after that, you have to answer a certain question, and invariably that question will end up involving some form of hypothesis on the distribution. Okay, so quite often in statistical analysis of data, you always are looking for that. Can you break down the analysis into some form of a hypothesis test, or maybe you break down the analysis into some form of an estimation problem? That's also fine. But even before that, invariably, you want to try and see if you can break down the problem into a hypothesis test. This is a design issue, and there's lots of things that will come into design. Now, design is not unique, right? You can do multiple designs, you can do all sorts of things, and it's sort of imprecise. There's no precise formula to say, no, this is what you do, this is what you do, this is what you do. And that will come later. But for now, we will look at scenarios where different types of designs people have done. So the way you learn design is to just look at all sorts of other designs out there, and then eventually you will get an idea of how to go about things. Okay, so that's what we'll do here. So here's an example. I'll deal with some 3 or 4 specific examples and ask you to think about it. Suppose there's a person who claims magical powers in being able to predict something. In India, it's very common, right? People claim this a lot. They claim I have this power, that power, and a lot of people go behind that also. Okay. Now, supposing you're a statistician and you're asked to design a statistical hypothesis test of some kind, or maybe some other statistical analysis to conclude whether or not this particular person has magical powers. How do you go about doing it? Okay, so this is a very typical scenario, isn't it? So this is a very interesting question. Here's another very, very common question. A lot of money rides on the second question, by the way. There's a company which claims that they have a revolutionary new treatment method for some disease. Okay, maybe not revolutionary, even a small treatment method which improves something in a disease treatment. It could be that. It could be a range of different treatments possible. And you, as maybe the ministry or government or some other person, you want to test statistically in a sound manner the effectiveness of this treatment. How do you go about doing it? There are established methods for this today. In India, this kind of proper measurement of treatment methods is not very popular. But if you go to other countries, they're very, very rigorous about it. They do careful testing, and only after that you get permission to market your pharmaceutical products. In India, there's all sorts of different types of things that happen here. Different traditional medicine of different types where people go and buy without a proper way of clinical trials and all that. We are not so strong on that, but statistically there are a lot of very well established methods on how to measure the effectiveness of treatments. Okay, so this is a very important problem. The third is, you may have data of this type. I'm putting out accidental deaths. It could be anything else also, right? You want to tackle a social issue or some issue of importance, and you're measuring something, okay? And over the whole year you measure it, and then you want to see if there is any pattern, like say seasonal pattern. Is it uniform over the years? For instance, accidental deaths, is every month the same, or are there some months which are worse than the others? So now why is this important? When you have seasonal patterns, you can go in and fix something, that month maybe, you double the number of traffic police on the road, or you double the traffic fee or something you can do when you measure it. I'm giving you accidental deaths as one information. It could be anything else. I mean, anything else you want to measure, like for instance, you're looking at a computer system or something which is crashing, and you want to measure it over a period of time and see, is there a pattern, is there a particular time when it crashes, or it seems to crash all the time uniformly. You need different approaches for different types of scenarios, right? So this is one more thing, finding some seasonal patterns, monthly patterns, maybe some other patterns of this type. Okay. Another very important and interesting question is questions of bias. Is there bias in the data? As in, for instance, supposing you look at data of hiring done by an organization. Okay, so this is an accusation you often get, that there is a gender bias, there's a geographical bias, there's a racial bias, there is this kind of bias, that kind of bias. Okay, and oftentimes it's people just accuse you, write all these great articles in newspapers, and everybody will forget about it after a while. But still, there is no. It's disappointing to see nobody does careful statistical analysis before accusing someone of bias. It's just, they just go for the headlines. So as responsible data scientists ourselves, we should look at this kind of thing, this kind of a question, and figure out, is there a proper statistical sound way of making some statements. So for all these questions, there are reasonably well established procedures that statistically will come out, and they change from time to time also, but in today's world there are accepted ways for testing out these kind of things. Okay, so in the next few slides I'll quickly walk through each of these things and try to pose it in some way as a hypothesis test. Some you may agree with me, some you may say, no, this is wrong, that's not the way to go about it, and that's fair. I think it's just a design issue, and we will pose it in some way. And then later on, when we learn all these standard tests, we will try and come back and attack these problems using our standard test armory and see if we can conclude something. Okay, so let's get started. First is this magical power example, right? There's a person who claims, let's say, to be very precise, that he or she can predict the throw of a die. You're throwing a die, a fair die, six-sided die, and this person with magical powers says, I can predict what it will be even before it shows up. Okay, so here's one possible way you can pose it as a hypothesis testing problem. You throw the die n times and you record the predictions. Okay, so you ask for the prediction, throw, ask for the prediction, throw, ask for the prediction, throw. You just keep recording it. Okay, prediction, actual, prediction, actual, prediction, actual, and so generally you tend to believe that the person doesn't have magical powers. So you want to say the null hypothesis is that the number of correct predictions is some binomial n comma 1 by 6. Does it sound reasonable? That if someone doesn't have magical powers and they are randomly guessing, right? So that's your null hypothesis. The null hypothesis is no magical power, random guess. Okay. So if you were to do that, every guess for every throw will be correct with a probability of 1 by 6. Okay, I'm just randomly guessing, so its probability is 1 by 6. So the number of correct predictions after some n trials will have a binomial n comma 1 by 6 distribution. This is of course assuming that the die is fair and the person doesn't have like some secret mirror and he doesn't see. I mean, all these things are built into it. It's in controlled conditions. The controlled conditions of the experimentation is extremely important here, right? So otherwise it doesn't make any sense, right? So if there's some wireless transmitter or something, then it doesn't enter the picture. Okay, so but this is your null hypothesis. The alternative is that this T is any other distribution. Okay, so this is the way I'm setting it up. You may want to argue about what is this any other distribution. It's too vague, it's too wide, it's too many. Okay, maybe you can be a little bit more precise on that, right? So this is after all 0 and 1 maybe. Okay, but still that's the null hypothesis, alternative hypothesis. Okay, so this is clear enough, right? So this seems like a reasonable statistical exercise to do. Okay, so notice for this you may come up with a significance level. You may know the probability with which type 1 error you may make. Maybe you may know, I mean, I'm not even giving you a test. Okay, so suppose somebody designs a test. For that test you can maybe calculate the significance level, maybe you can calculate the power for that test, but still that's not what you want, isn't it? what do you really want at the end of this test? You want a conclusion. So, okay, so this is the statistical setup, and suppose somebody comes and designs a test, right? What do you want from that test? You want significance level, you want power, all that is fine, but finally you want a conclusion, and more than anything else, you want to quantify the confidence of your conclusion. Think about that very carefully, right? And is the conclusion statistically significant? These are words that you want to carefully use and say that, you know, I've concluded this person has magical powers, right? And I'm very confident, I'm this confident about it, and these answers are statistically sound in some sense, okay? And you can imagine the number of trials n will be something important, right? If you do just one trial, it's probably not a good idea. If you do, maybe you can't do thousands of trials, but at least in a sound number of trials you should be able to do. And how does your confidence depend on the design of your test? How does your confidence depend on the number of trials? All these things are also very, very, very important at the end of this hypothesis test. So this notion of this confidence in your decision is coming in when you come to practice, isn't it? You have a particular test, okay, fine, you know that probability with which it makes type 1 error, probability with which it makes type 2 error, but that's not what I'm looking for. At the end, I'm looking for some confidence number. You know, I'm so confident that this is true, right? How do you quantify that? That part is very important here, right? Only then things make sense. You'll see this confidence will show up again and again and again in every proper problem that you design as a hypothesis test. Okay, so let me go through these examples once again. Supposing a company claims a new drug which say is effective in reducing heart attacks in some segment of the population. Okay, so here is a very typical way in which controlled clinical trials of drugs is done. Okay, so you get a bunch of volunteers. Now these volunteers will go to different doctors, and these doctors will be given two types of medicines. One will be the proper drug that the company does. The other will be some what's called a placebo. It's some sugar pill or some general pill which has no effect on anything. Okay, and it will all be random. So doctors themselves won't know to which patient they're giving what. Okay, but they're all volunteers, but they'll just look at them and they'll give one of these medicines. Okay, and roughly ahead of time, the medicines that you would have distributed to the doctors would be such that, you know, half of them are your drugs, half of them are the placebo. Okay, so roughly about, if you have n volunteers, n can go as much as like 10,000, 5,000 and all, you know, in big clinical trials. That's the sort of number. And about half of them get the drug, half of them get the placebo. Okay, and nobody will know. The volunteers won't know. Usually the giving doctors won't know. I mean, it's controlled in some other way. Okay, so after you do that, after a certain period of time, you've given this drug, maybe you're giving it regularly, and then over a period of time, you're measuring the results. Okay, you're observing the volunteers for heart attacks. Okay, so you'll have two different fractions now. The fraction of people in the first group, the drug group, which got heart attacks over a certain period of time. The second group, the fraction of people in the second group, the placebo group, which got heart attacks. Okay, so you have two fractions, and now your null hypothesis, once again, you remember the null is always taken to be the sort of the what is the base level, right? So what is the base level? Your base level, you're expecting the drug not to work. Okay, so that's the null hypothesis typically. So you will say F1 and F2 are roughly the same, or maybe even equal. I don't know. I mean, roughly the same is what you're going to say is the null hypothesis. The alternative hypothesis, one way of doing it, this is called relative risk or relative risk ratio or something like that. So you want to look at F2 minus F1 as a ratio of F2. Okay, so that number you want to say is some C. C could be, I don't know, 25%, 10%, whatever. So the effectiveness you can measure as a ratio like this. Okay, so the C can be given as 90%. So supposing if it's 90% effective, then you know you've really reduced significantly, isn't it? So you can see all that here. So this is the null and the alternative. So in the fraction of people who got heart attacks after getting the drug should be really, really low compared to the fraction that got only the sugar pill. And this difference you're going to measure as a ratio. I mean, you can do this differently. Some people will say dividing by F2 is not important. Just look at the absolute value difference between F2 and F1. You know, different people have different ways of doing it, but this could be one way, and this is one standard way in many medical clinical trials. This is used as a metric. Okay, so your null hypothesis is that the treatment doesn't work. Okay, your alternative is the treatment has certain percentage of effectiveness, either relatively or absolutely. Okay, in some sense. Okay, maybe. right? So even here, you need to find the C at which you will have good confidence about your conclusion. Okay, supposing if somebody designs a test for this. Okay, so somebody comes up with a way of testing it. Maybe you have reduced it to testing for mean. I don't know. I mean something like that. You have reduced it to. Okay, and then after that you will come to some conclusion. Actually, one sample will happen after the end of all these clinical trials. You will get one sample. You can put it into your testing. You will get a conclusion. And what use is that conclusion for you? I mean, how confident are you about your conclusion? Okay, that is what is more important, right? Somebody may say, I have the best possible test, you know, at some significance level, this is the power, etc., but for that particular sample that you actually got the data for, how confident are you about the result? That's very, very important. And does it depend on C? I mean, it will definitely depend on N, right? You can imagine more trials you have, more confident you're going to be. So more than designing the test with significance level, power and all that, once again the confidence of your decision ends up being vitally important. Okay, so this is the medical treatment. So let's look at pattern in accidental deaths. Here again you can tabulate it every month. Okay, so you want to hypothesize first that there is a constant rate, the number of accidents per day is a constant. Okay, so you want to say that, right? Every day there are maybe thousands of accidents and this 1000 is something fixed. Okay, and every month it is just, you know, the same constant rate repeating. Okay, so you may want to estimate some overall rate as theta, which is the total deaths divided by total number of days. Maybe you monitor this over a year, right? Over the entire year, the total number of accident and deaths in the year divided by 365 will be your overall rate. Okay, and then once you have a rate like this, what should be the estimated monthly deaths of because of accidents? In January it will be 31 theta, in February it will be 28 theta or 29 theta depending on the year. And then you have 31 theta for March, so on. In December you will have 31 theta. So this is what I meant by saying some sort of a multinomial distribution in some sense, right? So there's one theta and the estimated monthly deaths are of multiples of this. Okay, so the null hypothesis is the estimated deaths fits the observed deaths. So the null hypothesis you're saying is uniform. Okay, there is no seasonal pattern. Okay, the alternative hypothesis is the estimated and observed do not have a connection with each other. They are very, very different. They are significantly different. Okay, so there is a goodness of fit test here in some sense, right? You can sort of sense it. Does the data fit the uniform distribution? Okay, in some sense, that's what you're trying to assess here. And more than assessing and finding a theta and then coming up with something, how good are the estimated deaths? Do they match with the observed deaths? And how confident you can be is also equally important. Okay, so here is again an example where goodness of fit nicely shows up in some way. Okay, so let's go back to this gender bias in hiring example. So here is a typical what's called a cross tabulation. Whenever you have data like this, you want to do something called a cross tabulation. You want to say all the female candidates the company has interviewed, all the male candidates the company has interviewed, and then how many among the female got hired, how many among the male got hired. Okay, so how do you read this data? A total of 52 people interviewed with the company. 15 of them were female, 37 of them were male. Okay, out of the 15 female candidates who interviewed, 6 of them got hired, 9 did not get hired. Out of the 37 male candidates who got interviewed, 12 got hired and 25 did not get hired. Okay, so this is the data. Okay, now from this, what can you reasonably say about gender bias in hiring? Can you say something? Okay, so it looks like a interesting question to try and think of statistically. It turns out there is some sort of a goodness of fit type analysis here. Okay, but what is this? How do you pose it like that? So you can pose it like this. Okay, out of the 52 people who applied, assuming that they all have roughly the same skill level. So here are all assumptions, right? If the 52 people who you pick for the study, if they are all very, very different in skill level, then you can't make reasonable assumptions about distributions. Okay, you have to be very careful. So you have to think of some pre-screening that was done, and the 52 that came in have a reasonable chance of getting hired. At that level, you can do this analysis. Otherwise, the distribution is too vague. It's very difficult. Okay, so what am I going to do? I'm going to say I'll pick 18 out of this 52 at random. Okay, remember the 52 is split into two. There is 15 and 37. Two groups are there inside it. But out of the total 52, I am going to pick 18 out of that at random. Now, the number of males in this, females in this, all of this will follow our famous hypergeometric distribution. Okay, and the number that I am interested in, one number I could be interested in is m minus f. Okay, or if you want, you can take absolute value of m minus f, whatever. Okay, right? So m minus f, how many males I hired minus how many females I hired. If this number is going to be close to 0 in some statistically sound way, okay, then I can conclude that there is no bias. Or if the number that you actually got in this sample, right? So what is m minus f in this sample? In this sample, t equals 12 males hired, 6 females hired. This is 6. Okay. So if you pick 18 out of 52 uniformly at random, you will get some distribution. Okay, some distribution based on related to hypergeometric. Okay, so in that distribution, is 6 a reasonable number or is 6 an extreme number? Okay, so the null hypothesis is that the distribution of t is like this described before. You have this random sampling of 18 out of 52 and you have this m minus f, and the alternative hypothesis, there is some other distribution going on here. Okay, so how do you test this? You look at this number 6 for a particular sampling. How do you know how close you are to this distribution and all that? Some sort of is this sample 6 really from this distribution t, or is it very unlikely to be from this distribution t? Some sort of question like that is what you're going to ask. Okay, so so the 6 or the actual value that you're getting, is it likely to have come from the distribution of t that you expect when you choose from random, or is it from some other distribution? Okay, so slightly tricky aspect to this way in which this is phrased, but it's again possible to phrase this question in a statistically solid way as a hypothesis testing problem. So once again, more than anything else, you want to ask this question: is 6 a reasonable value for this distribution t? How do you quantify in this particular case? How do you quantify how close you are, how confident you are about this reasonableness, or is really a 6 a far outlier in this problem? Okay, so hopefully these 4 situations gave you a rough idea of how you look at some data and you want to make some conclusion, and how you can phrase it as a hypothesis test, how you should come, what are the metrics that are important finally when you want to convey your decision. It's not enough to convey your decision, you also have to convey how confident you are about your decision. Okay, so that's where this notion of a p-value will come in. Okay, so we'll see in the next lecture or so what is this p-value and how do you go about even finding it in some examples, and why is it that people believe it quantifies confidence in your hypothesis test. Okay, so we see that while we can take a practical question, pose it into a hypothesis test problem, it's not enough to just test something and conclude. Okay, people, when they want to accept your conclusion, they'll ask you for your level of confidence in the conclusion. Okay, and as part of the hypothesis testing framework, people use this notion of p-value to quantify the confidence in the results. Okay, so this is an important thing to understand how this p-value comes, and when you communicate the results of your hypothesis test, p-value is also often communicated. Okay, so we'll see this in the next lecture. Thank you very much.